Hello and welcome to this explainer. If you're tuning in, it means you're ready to tackle one of the most powerful and, let's be honest, mathematically dense techniques in control systems engineering. We are talking about designing a lead compensator using the bisector method. Now, I know the math can look pretty intimidating at first glance, but I'm absolutely thrilled to guide you through this. We're going to break down every single angle, every equation, and every little geometrical trick. By the end of this, you won't just understand the bisector method, you'll know exactly how to solve these types of problems yourself. So let's jump right in.
First things first, let's establish the core problem we're trying to solve. We have our plant equation, g of s, which represents an uncompensated system with poles sitting at 0, -4, and -6. And frankly, by itself, this system is just inadequate. Our ultimate goal here is to force the dominant poles to sit precisely at -2.014 plus or minus j times 5.252. To wrestle the system into submission and get those poles exactly where we want them, we're going to need a highly specialized tool.
Okay, let's dive into this. Before we get hit with the heavy equations, let's just define what that tool actually is in plain English. A lead compensator is a control system component that's designed to drastically improve how fast a system responds, its transient response, as well as its overall stability. It does this by injecting a positive phase angle, or a lead, right into the system's frequency response. Think of it kind of like adding a perfectly calculated steering correction to a really sluggish car so it handles sharp corners flawlessly. Here's the roadmap for how we'll get this done. First, the uncompensated system problem. Second, geometry of the bisector method. Third, calculating the compensator zero. Fourth, finding pole and system gain. And finally, validating with MATLAB simulations.
Section 1. The uncompensated system problem. Just to give you an idea of why we're doing all this math, consider the step response for our raw uncompensated plant, taking almost 140 seconds just to settle. I mean, you could literally go brew a cup of coffee waiting for the system to respond. In pretty much any engineering application, whether we're talking robotics, aerospace, manufacturing, a response time like that is completely unacceptable. And this is exactly why our heroic bisector method is required to speed things up.
Section 2, geometry of the bisector method. Now, what's really interesting here is the geometric roadmap of the bisector method. It acts as our Rosetta Stone, mapping out absolutely every variable we are about to solve for. Point P up at the top is our desired pole location. The method works by drawing a line from the origin directly to our desired pole, and then bisecting, meaning perfectly splitting that angle, to symmetrically place our compensator 0, which we call ZC, and our pole PC. To find exactly where those points land on the real axis, we simply have to solve for 4 angles: beta, theta, phi, and alpha.
So, if you're taking notes, here is your definitive playbook for solving any bisector method problem. Step 1. Use trigonometry to find those 4 key angles. Step 2. Use angle alpha to pinpoint your compensator 0. Step 3. Use your remaining angles to lock in the compensator pole. And Step 4. Calculate the raw system gain you need to power the whole shebang.
Section 3. Calculating the compensator 0.
All right, we kick things off by finding angle beta. Now pay close attention to the corrected calculation step here, because it's a huge trap. A really common mistake is to just blindly divide the imaginary part by the real part. But if you look at how the geometry is actually laid out, angle beta is calculated as the inverse tangent of the real part over the imaginary part. So that's 2.014 divided by 5.252. This gives us a beta of exactly 20.98 degrees. From there, theta is super easy. It's just 90 degrees plus beta, giving us 110.98 degrees. The big takeaway? Always double-check your geometric alignment before setting up that first tangent function.
Next up, we need to find phi. In control theory, phi is known as your angle deficiency. By evaluating the angle of our uncompensated plant exactly at our desired pole, we find it sits at -232.93 degrees. But for any point to actually be on the root locus, the angle has to be an odd multiple of 180 degrees. So we subtract to find the difference, which means phi equals 52.93 degrees. Translating that from math back to plain English, 52.93 degrees represents the precise amount of angular steering our new compensator has to provide to hit our target.
Now, we bring all these pieces together to solve for alpha, the angle that actually defines where our 0 will go. The geometric formula we pulled from our Rosetta Stone triangle is theta divided by 2 minus phi divided by 2 minus beta. We just plug in those numbers we successfully hunted down. 1010.98 over 2, minus 52.93 over 2, minus 20.98.
So the crucial point is right here. Angle alpha equals 8.045 degrees. I really want to emphasize this intermediate result because finding alpha is literally the key that unlocks the rest of the puzzle. If you get alpha right, your 0 and your pole are going to fall perfectly into place.
And here is exactly how we use it. To find the location of the 0, ZC, we use a trigonometric relationship. ZC equals the imaginary part of our desired pole, omega d, times the tangent of alpha plus the real part, sigma d. We plug in 5.252 for omega d, multiply that by the tangent of our hard one, 8.045 degrees, and then add 2.014. The math settles beautifully to give us our compensator 0 at precisely 2.755. Just like that, half of our compensator is built.
Section 4. Finding pole and system gain.
Let's move on and see how this builds. Finding our pole location, PC, uses an almost identical formula to the 0, but with one key difference. Instead of just using alpha alpha, we use alpha plus our angle deficiency phi. So we add our 8.045 degrees to our 52.93 degrees. We drop that combined angle right into our tangent function alongside our pole coordinates, and boom, we successfully pinpoint our compensator pole at 11.483.
All right, now for the grand finale of our calculations, the system gain, Kc. For this, we rely on the magnitude condition. This rule states that the absolute value of our entire compensated open-loop transfer function when evaluated at our desired pole has to equal exactly 1. We take all our derived values, our 0 at 2.755, our pole at 11.483, and our original plant poles, and we plug them all in. You calculate the straight line distances from each of the system's poles and zeros to our target, multiply the pole distances together in the numerator, divide by the zero distances in the denominator, and crunch that massive fraction.
And out pops this absolute beauty of a number, 425.34. Now this isn't just some random value. This single number represents the culmination of all our rigorous geometric and mathematical work. It is the exact, precise gain required to perfectly balance the compensator we just designed from scratch.
Section 5. Validating with MATLAB simulations.
Now it's time for the proof. First things first, we generate a pole 0 map in MATLAB using our brand new system. Visually, the x's mark the poles, and the circle marks our 0. This confirms that our calculated pole at negative 11.483 and our 0 at negative 2.755 have successfully dragged the root locus of the entire system exactly through our desired design point. We have perfectly corralled the system's behavior to do exactly what we want.
And this brilliantly illustrates our success in the real world. When we compare the sluggish crawl of the uncompensated system we started with, the one taking 140 seconds to reach its target, to our new compensated system, it's pretty mind-blowing. The new system rockets up and levels out in under 3 seconds. The transformation is literally night and day.
Let's look at the definitive, hard data from the MATLAB output to really quantify this win. Our rise time is now a blistering 0.29 seconds. But more importantly, our settling time, which, remember, used to be well over 100 seconds, is now exactly 1.9329 seconds. We achieved this absolutely massive performance boost while keeping a totally acceptable overshoot of about 22%. The math worked perfectly, plain and simple.
You've just walked through literally every step of the bisector method, taking what started as an intimidating geometry problem and turning it into a fully validated, high-performance control system. You know the angles, you know the formulas, and most importantly, you know exactly how to apply them. So, knowing how powerfully this mathematical tool can bend a sluggish, unusable system to your exact will, what engineering challenge will you tackle next? Thank you so much for joining me in this explainer. Keep practicing those calculations and stay curious.